Chapter 7, Probability Statistics, the third section, Sample Means. The first section we talked in general about the population distribution, the samples, simple random sample distribution, and the sampling distribution of sample proportions or means. 7.2 was the sampling distribution of sample proportions, and this one is going to be talking about the sampling distribution of sample means. So, what are the objectives? Find the mean and standard deviation of the sampling distribution of a sample mean. I hope you guys catch on to that. This is the sampling distribution of a sample mean. It's the distribution of a mean. All these means, the numbers come from different samples. Check the 10% condition before calculating the standard deviation, because if you don't have the 10% condition, that calculation doesn't mean anything. Explain how the shape of the sampling distribution is affected by the shape of the population and the sample size. If appropriate, use normal distribution to calculate probabilities involving sample means. So, here's two graphs. The one on the left is the population, household earnings in thousands of dollars. And if you look at that, down here the mean is just, I don't know exactly what that is. It'll tell us in a second. I don't know, it's around 60, 70,000. This is 100,000. Now, if you take mean household earnings from samples of size 100, I don't know how many samples they took, but each sample was size 100. You get to this graph, and if you look at the center of that, it looks like the center is about the same place as that one. So what does that mean? So when we record these variables, this is the household earnings, that's the variable we're interested in. Other such statistics like the mean, the median, or standard deviation we're interested in also. Sample means are among the most common. Consider the mean household earnings, sample size 100. That's this side. Compare the population distribution on the left with the sampling distribution on the right. So they took this population and grabbed a bunch of different samples of size 100, found the mean of each of those, and that was the data that they used to graph this thing. What do you notice? Well, let's see here. Both distributions about 70,000, 69,750. Both are bell-shaped. This one's a little bit cut off on the left. This one's pretty bell-shaped but skinny. The right has less spread. This is spread out from 0 to about 250,000. And this one goes from about 50,000 to 100,000. So when we choose many simple random samples from a population, and this is important, the sampling distribution of the sample mean is centered at the population mean and is less spread out than the population. Here's how they say it with the facts. Suppose that X bar is the mean of a simple random sample size n drawn from a large population with a mean mu, standard deviation sigma. They're going to use some subscripts here. The mean of the sampling distribution of the means, the mean of the means, is mu sub x bar, and it's exactly the same, mu. The standard deviation of the sampling distribution of all these x bars is sigma sub x bar, and they take the population standard deviation, divide by the square root of n. This can be done as long as you have that 10% condition. They always say n is less than or equal to 1/10 of the capital N, the population. It's easier for me to multiply this little n by 10 and make sure that my population is at least that. These facts about the mean and standard deviation, they're true no matter what the shape of the population distribution. So, if you sample from a normal population, things do not change. The shape of the distribution of X bar depends on the shape of the population distribution. If it begins as a normal distribution, then the the sampling distribution of sample means will also be a normal bell-shaped curve. This is true no matter what the sample size is. If you start with normal, it will stay normal. So suppose the population normally distributed with a mean mu, standard deviation sigma, sampling distribution of X bar has the normal distribution with the mean mu and the standard deviation of sigma divided by the square root of n, provided 10% condition is met. Most population distributions are not normal. What happens to the shape of the sampling distribution of sample means? Sampling distribution of sample means. I'm going to stop and say that over and over because that's sort of a mouthful. Sampling distribution of these sample means. When the population distribution isn't normal, well, let's take a look. It's remarkable that as the sample size increases, no matter what the start, the distribution becomes more normal. When the sample is large enough, you can guarantee that the sample means its distribution, no matter what the shape of the population, is going to be normal, as long as the standard deviation is finite. So, draw a simple random sample of size n from any population with a mean mu and a finite standard deviation of sigma. There's something called the central limit theorem says, when n is large, the sampling distribution of X bars is approximately normal. What does large mean? Well, let's take a look at this. Suppose you start with this crazy distribution here. You have 3 peaks, sort of like you have 3 bell-shaped curves. Suppose now you take the distribution of means 2 at a time. In other words, you take all the ways of taking 2 at a time from these things. You can take A and B or A and C, stuff like that. And you find the mean of all those, then you get this, which looks maybe a worse in one way. You've gone from 3 to 5, but it seems to be filling in these gaps. That's 2 at a time when n equals 2. If n equals 5, look how that's gone. Already it's filled in the gaps. It's starting to look normal. And when n is 10, it looks pretty darn good. When you get up to 25, it hasn't changed a lot. It looks really pretty good as far as a bell-shaped curve. But notice right down the middle, we've got this same mean of the means. That mean has not changed. But now it's a normal shaped curve. The spread has certainly changed. That's why we divide by the square root of n. So, how much does it take? You can start out with something very non-normal, and it looks approximately normal even with n equals 25. But we're going to make the number 30. If the population distribution is normal, then so is the sampling distribution of the sample means, no matter what the sample size is. If the population distribution is not normal, the central limit theorem tells us the sampling distribution of the sample means will be approximately normal if n is greater than or equal to 30. The central limit theorem allows us to use normal calculations using the normal CDF and normal PDF and all those, and the inverse norm to answer questions for many observations, even when the population distribution is not normal. So, we're going to do this and then probably have to end this first part. But if you take out your calculators and put in some things, we'll be able to sort of take a look at this. I've got my calculator sitting over here, and so if we turn on the calculator, then we're going to try something here. We're going to take this random int 1 to 100. We're going to store it into L1 instead of L2. So you go math, prob, rand int is 5, 1 comma 100 means we're taking a random integer from 1 to 100, comma, and put another 100 in. It'll take 100 of those, and close the parenthesis, store that into L1, second one. When you press enter, then it'll do that. It'll take a little bit of time, but there it is. So all of this is in L1. This is a random list. If you go stat and edit, you can see that data in L1. Second quit to get out. Now you're going to take this program and go down to your dot plots. And I'm not sure if yours is the same as this. It asks me which list. I'm going to say L1, second one. Yours, if it doesn't ask you, it'll run L1 anyway. Processing. And we'll see what we get, but it's probably not a normal distribution. Look at that, it's really crazy. Oh my gosh. Anyway, that's not very normal. What we can do, though, is take 100 of those lists. This random int 100, 100. Take a list like I just generated. Find the mean of that. Make sure it's an integer. And store it into L1. Now do that 100 times for this for loop. And here I just have a counter so I know how long to run it. And then it'll run dot plots at the end. Or you can just display it and you can run it yourself. But mine, I think I changed it so it would run. Anyway, let's do a second quit. And go find our program. I made this a program so I didn't have to type it in. Mean X bar. And run it. I'll get this memory thing. You may not have, won't get it. Let me see. Let me clear out. Oops, say quit first. Let me clear all lists, number 4, because it seems to run out of memory on me. And now, let me run that program. Now it's going to work on this, and it'll give me a count up here. What I'm going to do is put this recording on pause and come back after this goes through 100 of those. Okay. So we've made it all the way through the 100 lists, and it ran dot plots automatically. So I'm going to say I want list 1 because that's where I put all that stuff. When you press enter, now you'll see what it's done, because remember, it took 100 lists, found their mean, and then saved that mean into a list, and now we get something that's pretty normal looking. This bell-shaped curve we can start to see here. So, that's just one way of looking at these distributions. Let me put this away. We're almost out of time for this particular playing, so I'll hold it here, and then I'll be back with part 2, 7.3, Prob Stat.